Hello and welcome to Algebra and Composition with Functions. This is my second lecture of this type. If you would like to see another version, Math 1508, Section 1.8 is also Algebra and Composition of Functions, just on a different level, but some of the examples might be helpful. You can go back and forth between the two and find everything you need. My name's Tuesday J. Johnson, and I'm an assistant professor at Doña Ana Community College, a lecturer at the University of Texas, El Paso. This specific lecture was created for Math 120 Intermediate Algebra at DACC. Math 120 is also a course at New Mexico State University. I'm using Turner-McKeague's Intermediate Algebra, first edition. It's an XYZ textbook. It's a great textbook, a great resource. Chapter 3, Linear Equations in Two Variables and Functions. Section 3.7, Algebra and Composition with Functions. Start with some algebra. When we first started learning about numbers, we counted all the time, probably drove our parents crazy counting and counting and counting. And then we learned that we can add and subtract and multiply and divide. And then there's these decimals, and we can add, subtract, and multiply, divide. And fractions, and we can add, subtract, and multiply, divide. And oh my goodness, there's even negative numbers. And we can add, subtract, multiply, and divide. Well, now that we're in algebra, there's these things called functions. And it should be of absolutely no surprise that we can add, subtract, multiply, and divide functions as well. The nice thing is that it happens, right? The way we do these operations is as natural as could possibly be. To find the sum, f plus g, and evaluate it at x, we can find f of x plus g of x. To find the difference, f minus g of x, we take f of x and subtract g of x. The product is f of x times g of x, and the quotient also f of x over g of x, with a little caveat here. G of x can't be 0 because we can't have denominators that are 0. Don't overthink these. These are nice. This is what I call the mathematical notation, and this is what it really means. So I sometimes call it the real people notation. No offense to mathematicians out there. I include myself in that set. Just saying. So let's look at some examples. We're going to let f of x be 2x plus 1, g of x be 4x plus 2, and h of x be 4x squared plus 4x plus 1. If I want to find f plus g evaluated at 2, the very first thing I'm going to do is I'm going to rewrite it as f of 2 plus g of 2. And then I'm going to take it a step at a time. I'm going to find f of 2 using the function f. That's 2 times 2 plus 1. That's 4 plus 1, which is 5. Then I'm going to find g of 2. And g of 2 is 4 times 2 plus 2, which is 10. And then I'm going to make these substitutions. My g of 2 is 10. My f of 2 is 5. If I want to add them together, I'll get the value 15. So f plus g evaluated at 2, which is f of 2 plus g of 2, is 5 plus 10, 15. Over and over again, we're going to find g minus f at negative 1. So g minus f at negative 1 is g of negative 1 minus f at negative 1. First I'm going to find g of negative 1, which is negative 2. Then I'm going to find f at negative 1 using my function f, and that should be negative 1. When I find this subtraction, right, this difference, g of negative 1 minus f of negative 1, I'm going to replace negative 2, minus sign, negative 1, and a negative 2 plus 1 gives me a result of negative 1. G times h at 1. G times h at 1 is g of 1 times h of 1. G evaluated at 1 is 6. H evaluated at 1, yeah, we're finally using this big function. But 1's nice. 1 squared is 1. 4 times 1 is 4, plus 4 makes 8, plus 1 makes 9. So to find the product, gh at 1, I'm going to find g of 1, which is 6, times h of 1, which is 9, and 6 times 9 equals 54. We could do the exact same thing with division. It's really not much different. I just chose not to put an example on here for some reason. But you see, the four options, add, subtract, multiply, and divide, that we have for all those numbers, right? The natural numbers and the integers and the rational numbers and the real numbers, all of those operations we have for functions also, but we have a special fifth operation for functions that doesn't exist for numbers in general, and it's called composition of functions. A composition of functions is as follows. If f and g are functions, and if x is in the domain of g, and g of x is in the domain of f, then f composed with g, that's what that little open circle means, composed with g, is just, and I mean just, f evaluated at g of x. So composition is evaluating one function using another. Let's take a look at some examples. Going back to our same f, g, and h functions, if I wanted to find the composition f composed with g at -1, the first thing I'm going to do is I'm going to rewrite it. I'm going to rewrite it same order, f, g, -1, so that's f evaluated at g of -1. Once I have it rewritten into this form as evaluation, I'm going to work the inside out. I'm going to take g of -1. I'm going to find that. Alright, g of -1, that's going to be 4 times -1 plus 2. That's -4 plus 2, which is -2. So I know g of -1 is the same as -2. So instead of this ugly looking f evaluated at g of -1, I'm going to call it what it is. That's f of -2. Well, that's no problem. I know what f of -2 is. I can evaluate that. I just put a -2 in for x, so I'll get 2 times -2 plus 1. -4 plus 1 gives me -3. It is evaluation of one function, f, using another function. So, start with the inside, make your replacements, and work to the outside. G composed with h of x. This time I don't have a specific number, I have just x. Rather than substituting a value, we use the skeleton of g to evaluate at all of h of x. Oh, let's see what we have here. The skeleton of g says g of something is 4 times something plus 2. The skeleton shows the structure, so I remove the x's and I leave parentheses behind in their place. But what am I looking for? I'm evaluating g at h of x. So instead of calling it g of h of x, which is kind of confusing, I'm going to replace h of x with what I know it to be. I know h of x is 4x squared plus 4x plus 1. So I'm looking for g evaluated at 4x squared plus 4x plus 1. Okay, here's my skeleton. So in the parentheses, I'm going to put 4x squared plus 4x plus 1. Distribute my 4. 4 times 1 is 4, plus 2 gives me my 6 at the end. Rewriting the function with its rule and using the skeleton form is going to help the composition and keep it straight as to where you're going. H composed with g at 2. I'm going to rewrite it. H evaluated at g of 2. I'm going to work the inside. G of 2 is 4 times 2 plus 2. That's 8 plus 2, which is 10. I'm going to replace, instead of h of g of 2, I know g of 2 is 10, so I'm going to call it h of 10. And then I'm going to evaluate h. I'm going to take out the x and replace it with a 10. I have 4 parentheses, 10 squared, plus 4 times 10 plus 1. 10 squared is 100, so I'll have 441 as my value. H composed with f of x. Again, just an x. There's not a specific value we're using for the composition. I'm going to rewrite it. H, f, x, all the same order. I know that f of x is 2x plus 1, so I'm going to call it h of 2x plus 1. My skeleton for h, right, the function on the outside, my skeleton for h is h of something is 4 times something squared plus 4 times something plus 1. This is the structure. It's the bones of it. It's the skeleton of the function. And what I'm going to do is, in this representation, it's h of x equals. What I really want is h of 2x plus 1. So in the empty parentheses, I'm going to put in a 2x plus 1. 4 times the quantity 2x plus 1 all squared, plus 4 times the quantity 2x plus 1, and then plus 1. I would encourage many of you to write this out. 2x plus 1 squared. Remember, that's multiplied by itself. It's really easy to forget about some middle terms going on here if you just square the 2x and square the 1. So write it out, multiply it out. When we multiply this out, we'll get 2x times 2x is 4x squared. Here I have a 2x, 2x times 1, and here I have a 2x, gives me the 4x in the middle, and 1 times 1 is 1. 8x plus 4 plus 1, this 4 plus 1 makes a 5. When I distribute my 4 times everything in parentheses and combine like terms, I'll have 16x squared. 4 times 4x is 16x, plus 8x makes 24x. 4 times 1 is 4, plus 5 makes 9. So simplifying is the hard part here. Doing the composition, not so bad, but if it has to be simplified, that's where your algebra skills kick in, and you need to take your time and write it so that you can follow it. So we could also use tables to find sums, difference, products, quotients, and even compositions. Let's see how we do here. F plus g of 2. That's f of 2 plus g of 2. First step is always write it as, quote, a real person would. So f of 2 in the table for f, when the x value is 2, my y value is 0. In the table for g, g of 2, input is 2, my x value is 2, my y value is 1. Let's color code this a little bit. F of 2, and that gives me 0, whereas a g of 2 is going to give me a 1. 0 plus 1 is 1. Now, I can't do those colors for every single one of these examples, or else it's going to be just nothing but lit up colors. So let's follow along. G minus f at -1. First rewrite it. G at -1 minus f at -1. So I'm going to start with the table for g. When x is -1, my output is 2. Minus sign. F at -1. When x is -1, f is 1. 2 minus 1 is 1. Done. F times g at -3. That's f of -3 times g of -3. F of -3 in the table for f. When x is -3, my output is 4. In the table for g, when my input is -3, my output is +3. 4 times 3 is 12. G over f of 0, that's g of 0 over f of 0. G of 0 is -4. F of 0 is -2. Make sure you divide in the correct order. -4 over -2 is +2. Now, the composition. You can do this. F composed with g at -1. I'm going to rewrite it. F, g, -1, couple of sets of parentheses. F, g, -1. So I'm going to do this part in blue. G of -1. In the table for g, my input is -1, my output is 2. So instead of calling it g of -1, I'm going to call it 2. This is like when your mom uses your full name, you know you're in trouble, but when you're hanging out with your friends, it's like, whatever. So f of g of -1 is the same as f of 2. Well, if the input into f is 2, the x value of 2 in the table for f gives me an output of 0. Using tables for algebra and composition of functions. We could also do the same with graphs. F plus g at -1 is f of -1 plus g of -1. Here's my graph for f. When x is -1, my y value is 1. Here's my graph for g. When x is -1, my y value is -2. 1 plus -2 is -1. Don't overthink it. Remember, I want the outputs. I want the y values. G minus f at 4. On the equation for g, g of 4 is 2. Minus sign. F of 4. On the graph of f at 4, I have a -3. So 2 minus a -3, which is 2 plus 3, gives me a value of 5. Composition can also be done with graphs. If I have f composed with g at -4, remember that's f evaluated at g of -4. We're going to start with the inside. G of -4 is -1. So instead of using the full name, g of -4, I use the nickname -1. Now I'm looking for f of -1, so I switch to the f graph. At -1, my output is 1. F of -1 equals 1, therefore, f composed with g at -4 is also equal to 1. That's algebra with functions and composition. Thanks for listening.